Okay. Can you see my presentation?
Yes, I can see it. It's not in full screen, but we can see it.
So like now you should hopefully see it in full screen. Right?
Not yet, at least for me.
No.
View. Does it work?
Now it's working. So.
Okay, perfect. So thank you very much for the introduction, and sorry for the technical problems here. So like I wanted to give a presentation on the ongoing actuator line modeling that we're doing in the University of Twente. So like just as Bruno was also saying in his talk, this is like ongoing work. And like it's a similar kind of work. Like we are looking at large eddy simulations and then specifically trying to improve like actuator line modeling in these simulations. Okay. Is it still working for you?
It's only, I can only see the first slide. Now it's moving.
Okay, perfect. So I guess I cannot go in play mode. So the wind farm dynamics are given by like dynamics at like very, very different scales. So like here, like I basically took a sketch from a recent science paper on this, showing like the wide range of scales that is relevant in wind energy applications. So like basically ranges from the flow dynamics directly over the blades up to the flow dynamics around the turbine. So we will see some of the presentations in the HPC projects during this meeting will be on blade dynamics, later today by motion, for example. Like this presentation, just as Bruno's presentation, will focus on some of the turbine modeling that we're doing in the project. And like in some other projects, we are also doing like wind farm modeling, which is basically indicated over here. It's like if we're doing like the modeling of a single wind farm, and you could potentially even go to even larger scales, modeling the interaction between different wind plants and sort of see like how much that would influence the performance. So like what we're doing is like actuator line model simulations, or like large eddy simulations. So what we're doing is like a simulation with a well-tested large eddy simulation code aimed for atmospheric boundary layer applications. And for this reason, it's pseudospectral in horizontal directions and finite difference in the vertical directions. It's horizontal periodic boundary conditions, which will give some complexity. And if we want to actually model wind farms or like turbulent inflow on a wind turbine, so I will shortly address this as well. And then like boundary conditions would be adjusted based on the problem under consideration, and then there would be several advanced options for like the subgrid modeling in these large eddy simulations in order to use computational time as efficiently as possible. So like in some other work, we're doing big wind farm simulations. So like I'm showing here like a visualization of like one of these large wind farm simulations. So like instead of like using an actuator line model over here, there's like an actuator disk model for the turbine. Since like on these large scales, it's very challenging to do this in actual actuator line modeling. And like what we see over here is like a flow coming in from below. The blue regions are indicating low velocity wind speed regions, indicating the wind turbine wakes that are formed behind each turbine. And then like further downstream in the wind farm, we see the interaction between these different wind turbine wakes. So we see that especially in that region, the dynamics become like very, very complex. And then these white particles over here indicate tracer particles that are following the flow, showing like how turbulent this flow is. And this is like basically one of the reasons why we're using these time resolvent simulations, justifying the need for high performance computing. And like the large range of scales in wind energy applications make that there's like different ways of modeling the wind turbines. So like if we're looking at these large wind farm scales, we would be looking at like actuated disk simulations. It's an efficient method in order to incorporate like the large scale effects of the wind turbines on like a flow like in a wind farm. There would be like a sort of like a hybrid method between like actuator line and actuator disk, which is like an actuated sector method, or like actuated disk with rotation. Or like we can do like the full actuator line method where we have like the full details of the blades incorporated. And basically like one of the goals of the project is to sort of like understand like how much more can we understand of the flow if we are like applying this actuator line model. So like we would have like more information on like unsteady turbulence loading on these blades, and more details on like the tip vortices and so forth. And like in the actuator line model, what is being modeled is like the lift and the drag force on these turbine blades, like calculated at each point at the blade over here. And like this would be using tabulated coefficient values for that are characterizing the properties of these blades. And like these are either obtained from measurements or can be obtained from like blade resolve simulations. So this would basically be related to some of the work in this HPCWE project, some of the work performed in Imperial, where they would do these blade resolve simulations, and then these updated coefficients could be used in these actuator line simulations. So like here, like basically, there's this an additional sketch where we sort of like indicate the these different forces, how they are determined based on the incoming flow speed, taking into account like both the blade rotation and the incoming flow speed. And like one of the aspects that is relevant in these actuator line simulations that we want to further study is like what the effect of the smearing of these forces is. So like these forces are like calculated locally at each blade point, but for numerical stability we need to smooth out the forces in order to prevent too many numerical oscillations in these large eddy simulations, which is especially relevant in the combination with spectral methods. And like one of the goals is to sort of like understand like what is the effect of this this smearing, which is like generally performed using this exponential function over here. And then like one of the key parameters, and this is like the epsilon parameter, which at the moment for numerical stability we have to set at 2.5 times the grid spacing that is employed. But this smearing is both computationally intensive and may not scale so well. So the question is whether we can do smarter scalings that are also representing the physics appropriately. So this is like some of the things that we want to address. And we want to see like how well, what is the difference between like wind turbine simulations and like actuated disks. So like here, there's like some comparison performed in Delft. So this is based on wind tunnel experiments of both an actuator disk and a turbine. And then we see that like if we're having an actuated disk approach, this experimental data, we see that like a disk would give like very different flow statistics in the very near wave. So like basically at the left plots that we see over here. So if you can see my cursor over here, so in these plots we see that there's pronounced differences. If you're looking at the wake somewhat further downstream, we actually see that like disk and turbine give like reasonably similar results. So this is also one of the motivations of the use of actuated disk in like very large wind farm simulations, but still, of course, we can get more detail with actuator line simulations. And this is some visualization showing actuated disk model simulations capturing the effects as observed in the experimental data. So like these simulations can agree very well with high performance measurements that are being performed. So like this actuator line model, these actuator line model simulation, we also want to compare both against like reference literature data for like the NREL 5 megawatts turbine, as well as like some wind tunnel data. So like I will present some of the initial results on that. So like the first case that we're looking at for like actuator line model is the NREL 5 megawatts case. So we use the data from the NREL report over here, and like we use the tabulated data given in the table over here to represent the wind turbine blades, and then like we use like a uniform inflow with 8 meters per second in a large domain so that the flow can fully develop, using a grid of like 768, 192, 384 as indicated over here. And then the turbine is like placed like far enough into the domain in order to prevent like the induction effects to have like too much of an effect on the flow dynamics observed at the blades. So in these plots we compare the actuator line model results as implemented in our code now versus some previous results published in literature in the reference over here below. As well as like BAM model results. And then we see that there's like very good agreement for both the angle of attack as well as the axial velocity at the blade locations. So this is axial velocity here on the vertical axis and the blade location here on the horizontal axis. Also giving fair agreement with the BAM model predictions. And like here we have the same for like the as function of radial position in the blade, the lift force and the drag force, giving a good agreement with previous simulation results as well as the BAM model. And then we have the same here for like some downstream positions, like showing the wake structure over here. So like one pronounced thing that we can see in these plots is this sort of large scale jets at the root location. So this is for this particular reference case, the turbine nacelle is not included. So like this is also like something that we want to test, like how much of an effect does this have, and we have already seen before that this has some effect on the flow, and this we will compare or like add later if we compare to some wind tunnel data. And like these plots over here show the streamwise velocity as function of downstream position of like this newer simulations versus previously published data, showing very similar development of the flow. And this is Spanwise velocity, so we see the blades or like the wake rotation being captured in these simulations, as well as the development of like turbulence intensity in the flow, like which is mainly being formed like towards the end of the wake, because like there's no turbulence inflow in these simulations at all, and then the turbulence intensity in the wake is like only developing later on in the flow, being quite dependent on like the numerical scheme that is used, how quickly this turbulence intensity forms towards the end of the wake. So in recent work, we're like also trying to sort of see whether we can validate this against wind tunnel experiments in order to get a better feeling of like how well these models are doing compared to wind tunnel data. So like for this, we're simulating a turbulent boundary layer. We're taking the setup as given over here, and we'll compare to like some of the wind tunnel experiments that are performed in the EPFL lab in Switzerland. Placing one turbine over here, relatively close to the inflow, but still like far enough away to prevent induction to be too close to the domain. And then we use what is known as a concurrent precursor technique in order to model the inflow inflow turbulent boundary layer for these measurements. And we have like a large domain afterwards in order to see the downstream development. So like since we have this pseudo-spectral code, like modeling these inflow conditions is a little bit tricky, and we do this by doing two concurrent simulations, in which one simulation is like performing a turbulent boundary layer without any interruptions. Like this, the domain given over here on the left, doing like either a turbulent boundary layer or atmospheric boundary layer simulation separately. From this simulation, we sample data at the end part of the domain, and this we copy to the other simulation domain, where we either put like a wind farm or like a wind turbine in this case, where it accesses the inflow conditions. So like we copy this to the end of the domain, given the periodicity of that domain, it accesses the inflow over there, which you can see in this representation over here, where we have like the turbulent flow that we generate in this additional simulation is impinging on the wind farm or the wind turbine that we sort of put there, and this allows us to capture these turbulent boundary layer dynamics very accurately in order to reproduce experimental data. And then the model wind turbine that is used in these experiments that we are comparing to is given by this model wind turbine number that is given in the top here. So like we use again like tabulated data, but now like tabulated data for the experimental data that we are comparing to, and this we plug into our actuator line model. And then what we compare over here is like, yeah, how well does the actuator line model, how much benefit does this have compared to the actuator disk model simulations? So we have like different plots given over here. So on the different plots are given like data for like different downstream locations. So this is like the this plot here on the left over here is the inflow condition just before the turbine, and then like the different additional panels are given are giving the flow profiles at different downstream locations behind the turbines, like 2, 3, 5, up to 20 turbine diameters downstream of the turbine. The data points here are giving the experimental data points that we take from this experimental paper over here. And the blue line over here is giving the actuator disk model results, showing that, again, we capture the downstream dynamics accurately. Like the near wake is not captured so accurately with this actuator disk model approach. And this is like two reasons. So like it has like to do with like using the actuator disk model instead of the actuator line model. And what we saw before is that we need to incorporate the turbine nacelle and tower in there. So we tested out these things separately. So we have in this case, like actuator disk model plus structure means that we are separately also modeling the nacelle and tower, and we see that this gives improved results, but like it's not perfect yet. For the downstream locations, it's still quite good. If we do just an actuator line model, we see that it captures like some of these things in the near wake at least better than like the actuator disk model without the nacelle. But like we get the best results when we do like actuator line model plus this tower and nacelle, showing that like it's important to have like for the near wake both actuator line model in there as well as the turbine nacelle and tower. And this can be done even on like reasonably coarse resolutions if you do this on compared to these wind tunnel experiments over here. So like this is the mean streamwise velocity that we are comparing over here. So like if you want to look at some more detail, we're looking at the turbulence intensity or like standard deviation. So like again, we are looking at the different downstream locations. So like the actuator disk model is actually capturing these increased turbulence fluctuations at the top of the blades surprisingly well. We also see that here in the near wake at XD/2 that there's like additional fluctuations like close to the nacelle area, and this sort of smooths out like further downstream in the wake. So like if we add the nacelle and tower, there's some additional change over here, but like not so much, most likely due to the limited resolution that we have at the moment. And we also compare to like actuator line model simulations that for these turbulence intensities here give like similar results as the actuator disk model, but still agree like well with the experimental measurements. So this is what I wanted to present today. Like, if there's like any questions, I would be happy to take any questions. So thank you very much for your attention.
Thank you, Stevens. If anyone wants to ask something, it's the moment.
Hi, thanks, Richard, for the nice presentation. I'd like to ask you two things, actually. Is there any significant difference between the actuator disk model and actuator line model in terms of computational cost? So that's the first question. And the second question, how do you think this agreement with the experiments in terms of the turbulence quantities could be improved? I mean, it's quite good, but there's still some differences in terms of these